Okay, now it's official. So I welcome you all to the session from the Photon and Neutron Science Interest Group, Converging PaN FAIR data around the world. So as you can see on the agenda slides, we have basically two blocks of presentations. The first one, so what we observe in the Photon and Neutron community recently is that there are national projects popping up here and there. And we wanted to give some of them an opportunity to present what they are doing so that we can see whether there is, say, option to collaboration. And in the second block, we will consider a special case, X-ray absorption spectroscopy databases. And there we have examples from Japan and one example from Daphne, or wherever you want to locate that, that is in the making right now in Germany. Yeah, and we agreed that we take questions to the presentations at the end of each blocks. So then I already asked Juan Bucaré to present the work from PSDI.
Thanks, Ralph. Hi, everyone. And when I started this, so I'm Juan. Now I'm in Costa Rica, I'm Juan Bucarregui. If I were in England, I'd be Juan Bucarregui. It's a slight difference. And I'm leading the PSDI project in the UK, which, as it says in the title, is about building a data infrastructure for the physical sciences. Physical sciences to us means chemistry, materials, that kind of physical science, not high energy physics or astronomy or anything like that. Thanks, Rolf, for the invitation. The project is led by our department, Scientific Computing, at the Rutherford Appleton Laboratory, part of the Science and Technology Facilities Council, and the University of Southampton School of Chemistry. My colleagues are listed there. I won't name all the names, but I guess you know some of them. Yeah, I think that's all. Let's move on. Next slide. So the aim of PSDI is to build a data infrastructure that connects existing experimental and computational facilities in the physical sciences and connects with data that's relevant to the physical sciences, but coming from elsewhere, and also taking physical science data out to other communities who may want to use it. It's a bit of an aside. I'm a sort of imposter in this meeting because it's not specifically about photon and neutron generated data, right? In terms of the NFDI projects, we've probably got more in common with NFDI for Chem and with the materials project than we do with the Daphne project. But other parts of my department do work extensively with the photon and neutron facilities that we have at the laboratory. And you've seen my colleagues give presentations to this interest group before. But obviously there is a big overlap. So in this aim, I'll emphasize a few words. So it's about connecting existing infrastructures. We're not about throwing everything away and starting new, building something new. It's about what's the glue we need to bring different data infrastructures together. We're doing experimental and computational data, so from computational chemistry, etc. And we want to build, it's four sort of main areas. A platform where we can collect the data, share it, aggregate things, add value by bringing two things together, integrating them, and curating the projects. And the curation word's clear in this last point. It's about sustaining the data beyond the lifespan of individual projects. A lot of data is developed in a project, used for a paper, and then never found again. We want to support the analysis across experimental, simulation, and reference data. So I mentioned the experimental and simulation up here, the computational stuff. Reference data builds on a service we've been running for very many years in chemistry. I'll talk a bit more about that later. It's called PSDS, Physical Science Data Service. So the two names are deliberately similar. This is an expansion of that other project that we've been running for many years. Next slide. So one of the things we observe in kind of motivating the project is that there are what we called 4 pillars of infrastructure out there. There are the large sort of national and international facilities represented here in force. And in the UK, we have our own, of course. The things we're calling national research facilities, they used to be called mid-range facilities. This is sort of colloquial funder speak in the UK. And there's a whole bunch of those. They each have a separate data infrastructure. PSDS that I mentioned is one of them, but there are others in other areas. Computational initiatives, there's a very, very long list here. We've got a program in the UK called the Collaborative Computational Projects, which has been running for decades. It's very successful. It brings together people from different universities to jointly work on code and sustain and curate that code in various areas of computational chemistry. The first ones were numbered, so it wasn't very transparent. The later ones are, QC is quantum. It's like they started picking up names, so you can understand them a bit. Haven't got time to go into all that. And of course, the research that's going on in the individual labs in the chemistry departments around the country. Next. So I won't dwell on this. It's in this audience, it's kind of obvious what we want to do. I think we want to enable the sharing of data, software, and models. We want to be able to combine data from different sources. We want to integrate experimental and computationally generated data with the reference data, providing close data computation, make data ready for AI. That's a phrase you hear a lot these days. Exactly what it means, I don't know. I used it in the project proposal, but it means make data ready for AI, whatever that is. Obviously, we're in an open science context, and quite a lot of training and guidance is also needed in the community to. We recognize, and I'll talk more about this later, that the cultural change is almost is bigger than the technical change. The hard job is in changing the culture in the domain. Next slide. Do give me a warning if I'm running over you. So the project timeline, well, we had some predecessor projects over, like it's 50 years now that we would be, this origins of this project, the Chemical Data Service, Database Service began in '74. That ran for many decades, and then we had PSDS, which I mentioned, but the current PSDI project started in 2021. We put in a statement of need, we socialized the idea, we got a project, or we got a phase of project to develop and really make the initial release. We're getting towards the end of that, and we're aiming for a release in April next year, a version 1 release. Next click. That's nice and simple. The reality was very much more complicated. No one's fault. We've had lots of very short projects because that's the way the funding came. It's made it rather difficult. But you can see lots of small things, including gaps. And then only fairly recently did we start getting substantial funding. And now we're in the middle of this better block where we actually have got good amounts of funding. Next. We structure it into 7. One more click, please. One more click. And I won't go into the details, but it's basically stuff around the people, stuff around the data, and stuff around the technology. As I said, it's largely a people problem. So we've got community engagement activities, training, requirements capture, etc. We've got to manage ourselves, and we've got to have a stakeholder-driven governance and all the things that entails. Then we've got the data layer where we're collecting data from different places. We're collecting is not the right word. We're not moving data. We're just indexing across, so to search across other open data sources, internal data that we're generating ourselves, these licensed collections from the PSDS service, and then knowledge bases and toolkits are also going to be served through our infrastructure. And then we have the technology layer where we're developing the gateway with the front end and the user management and the admin. We're doing the platform, which is a whole load of data, sort of first layer hardware and operating systems, time database type of layer, and then the data services on top of that. And I'll give an example of that later. Next. So this is our vocabulary. For all the stuff that isn't technical, we call it the hub. So the organization that will support this is called the hub. The pathfinders are our case studies that are driving the development of the platform, and the platform is all the technology that will underpin the data. Next. And maybe the top and bottom layer, hopefully you do and you carry on, but it doesn't grow. The data will grow over many decades, hopefully, right? So the examples we've got in our pathfinders are just small examples. We're using them to drive the requirements for the platform. They will be useful in themselves, but the canvas that we're playing on is huge. So it's no way going to be comprehensive. It's just a few dots. on that picture. Next. We have an architecture. I won't go into detail, but basically the gateway is the front end and the user management behind it. We've got a bunch of data services, the minimum set required to support the pathfinders at the moment. And then we have our pathfinders, and I'll give you some examples later. We have external data sources that we're linking through to, and we have the licensed data collections that are currently in PSDS. Next. 1 minute only. Okay, sorry. Common search. I'll just give a very quick example. Next. We're putting in place a common search across these internal sources. Some of them were created ourselves, some of them created in Pathfinders. We're using the Optimade API to access 29 other databases through that. That was a really easy win for us to implement that API, and suddenly we can search across all these databases, and we're doing these referenced collections. Next. We're doing a number of Pathfinders to try and drive it and to actually have something of value at the end of the day. One on experimental data capture and XAS data in particular, and my colleague Abraham is doing that. And I think Abraham may have spoken at one of these meetings before. Don't ask me too much about that. I'm not so close to it. Doing stuff on process recording, on how to build collections, on process orchestration, and on how to turn data into knowledge using machine learning, with a specific example driving that. And I'm probably out of time, so I won't even go into the examples. Just click through to the very last. Keep next, next, next. These are the examples. Next. 2 or 3 more. Oh, sorry. I just want to show the last slide. Not that it's very important. Next one, next one. One more. This one. That's my last slide. And that's the state we're in at the moment, right? We've got a few bits. Even release 1 will be like this. We've got some things sorted out. We've got a few bits that will be working, but we've got a big canvas that is not yet in place. Thank you, Rob. Sorry for that.
No problem. One remark on, say, what it means to be AI ready. People say FAIR stands for fully AI ready data. Okay, the next contribution is by Lisa Amelung and Matthäus Theodoro, which we stay in Europe, but now go to Germany. We report on the Daphne for NFDI project.
Thank you, Rolf. Hi, everyone. It's my absolute pleasure to not only introduce the Daphne project to you, but also to introduce Matthäus to you, who is a collaborator in the Daphne project. He's working at European XFEL, and yeah, which is one of the institutions in Daphne for NFDI. And I'm Lisa. I'm the project coordinator of this project we would like to present to you. And I'm working at DAISY in Hamburg, so we both come from Germany and work very close to each other, not only in distance of the institution. So today we would like to talk about PIDs and metadata in Daphne for NFDI. But before Matthäus goes into the details, I would like to tell you a bit about the project. Could you please move on? So Daphne for NFDI stands for data from photon and neutron experiments. And as I can tell you, this is the basis for many scientific discoveries and innovations. I guess you all know that because you're working in the field. Yeah. We just brought some examples which are pretty cool and show how many things can be investigated throughout the data from photon and neutron experiments. So yeah, this is what Daphne stands for. Could you move on, please? One more. Who is Daphne for NFDI? Out of my perspective as the project coordinator, I can tell it's a great team of people. It's IT people, scientists and users who work together in the project. We are funded by the German Research Foundation, which is called DFG, and we are part of the National Research Data Infrastructure, NFDI. And if you want to know more about NFDI and also other projects in NFDI, you should join our Birds of a Feather session tomorrow afternoon to get to know us, yeah, the NFDI. In total, in Daphne, we have 18 funded partners, 11 institutions, 11 universities, sorry, and 7 large-scale research facilities. And yeah, we have more than 100 participants throughout Germany and Europe. And yeah, the whole thing is coordinated by DAISY, the place I work in. Yeah, could you move on? The main heart of the project is our use cases, which serve as flagship projects to showcase how fair data and investigations into fair data can make a change and can make things easier also for the next PhDs, postdocs, decades, and so on. And we have brought two examples today. One of them will be showcased later by Christopher, and Matthäus will talk about the XPCS use case, at least a bit. Could you move on? So this is just to summarize what Daphne does or has already been doing. So we enter many topics that concern fair data, and if you want to know more about the project, feel free to reach out to our Zenodo or feel free to reach out to me. But now I want to hand over to Matthäus, who will talk about the technical bits.
Thanks, Lisa. So you can go to the next slide, please. Yeah, so before I go and talk a little bit about the XFEL, I'm going to talk also about some initiatives within Daphne towards fair data that I think are quite interesting for us to at least have a look at and know that they exist in the first place. So first, I'd like to talk about metadata. So we're talking a lot about fair data, but metadata is also quite important piece in order for data to get fair. For instance, what I see as metadata in my home institution in the European XFEL is different from the definitions that Lisa, 3 kilometers away from me, have in DAISY. And within DAISY or within the European XFEL, we already disagree a little bit between what is metadata when it comes to different users, right? We are a user facility, we have hundreds of users coming every year, so hello. So yeah, definition of metadata and having this a little bit more standardized when it comes to PaN sciences is crucial to have fair data across different facilities and different users as well. Therefore, within Daphne, we released a white paper on metadata that you can find in that link over there. But yeah, the goal is, again, to compile recommendations when it comes to metadata within PaN sciences, right? And the reason for that, well, I'm not going to say it again, but it's for having data more fair at the end of the day, right? To do it so was hard work because, again, we are a lot of users, a lot of facilities, a lot of universities, and everybody has a different idea on this. So we had to gather what is the status of the community and find common grounds and then compile the metadata white paper that, well, you have a snapshot here, but you can find it in the DOI. And talking about DOIs, you can go to the next slide. Persistent identifiers. So this is another topic that is rather important when it comes to fair data, right? And this is also something that we in Daphne have been discussing a lot about it. So persistent identifiers, they come in different shapes and sizes, right? For instance, for people or organizations, you can have ORCID or ROI, ROR. For publications, you usually have DOIs. For instruments as well. For samples, you have IGSNs. And yeah, so at the end of the day, within Daphne, we are trying to follow up some outcomes from Expanse, another project that came before us, and try to get some knowledge of how people are doing this and try to implement this better in different facilities and for different users. You can go to the next slide, and that's the topic that I get closer to my home facility. Let me just, yeah, I have time, which is the European XFEL. Again, European XFEL is a large-scale free laser facility, right? And yeah, we have different instruments, we have different users all year long. But we do have a nice, at least in my opinion, but I'm biased, of course, IT structure. And I brought a little slice from what we do there regarding IT. Of course, it's much more complex, but I brought what's important with the scope of this talk right now. So I was talking about metadata. We have our own metadata catalog, which was developed by us. And, well, we do have DOIs for our proposals. That's nice. We have PIDs already for that. We have general proposal information that one day we can benefit from the Daphne white paper as well, modifying some stuff and looking at the outcomes from the white paper. We also have access to the raw data through Globus, our metadata catalog, and so on. But another nice thing that we have in the European XFEL is DAMNet. DAMNet is a tool that we develop ourselves as well that comes with automatic, well, semi-automatic collection and processing of data and metadata, right? And this is nice when it comes to sustainability, because when you think about being time that time is of essence, right? So if you can make right decisions during the experiment, looking at data that is almost online processed, then you're also getting time, right? And this also comes with some metadata and metadata annotation that can benefit from Daphne. I'm not going to enter in details in the e-log, but we do have a new e-log recently developed. So it's also important because within Daphne, we're also making electronic notebook white paper. Can you go to the next one, please? So a little bit more on initiatives within the European XFEL. As Lisa mentioned, we have the XPCS use case together with University of Zingen. So XPCS is correlation spectroscopy, right? So data is usually huge. It's yeah, outstandingly huge. So right now we are having a collaboration with University of Zingen that happened through Daphne, in which we are planning to use our Deminet tool that already have kind of nice structured, reduced data, and sending this to this open platform that they are developing at their university to make data open, upon request of the user, of course, at least now. Another thing that we're moving more towards fairness is the Nexus format, right? So this is quite standard, and we're trying to, again, we have different techniques happening in our facility. And for different techniques, we have also different Nexus standards. So we're moving towards having more ways of outputting Nexus in our beam line. And this is also kind of inspired by Daphne. So last topic, data reduction. Please, data reduction is very important when it comes to sustainability. In a facility like the XFEL, it's like petabytes per day. We have to reduce that somehow. And we have a new data policy that got also a lot of feedback from Daphne or other facilities and other users within Germany. And if you want to have a look, I can send you a link as well. It's published already, or a new data policy that is moving towards having data more fair and more reduced, which is crucial as well. So, sorry, Lisa, you can finish.
Yeah, let me just use the last, I don't know, seconds. Could you move on, please? To invite you to our annual meeting next year. So if you want to meet the team, you have to come to Berlin, Germany. Weather is comparable, I would say. Let's see if it's that warm. Yeah, thanks. Yeah, and with this, yeah, thank you for joining us and like taking this short look into Daphne for NFDI. And if you yeah, want to contact us, there's some contact data of our speaker and myself. So yeah, thanks.
Yeah, thank you very much. So with the next contribution, we jump over the Atlantic to this side of the Atlantic. And we go to the US with Brian Maravin, who will tell us a little bit about what they're doing at NIST. Could you, the other slides? 1C. Yeah, this one. Brian, are you with us?
Yes.
So the floor is yours and
Okay.
go ahead.
Just waiting for the slides. Are they up there or? Yeah. Ah, yes. So good afternoon or whatever time it is where you are. Thanks for the opportunity to talk here. My name is Brian Moranville, and I'm coming from, yes, at the National Institute of Standards and Technology in Gaithersburg, Maryland. Let me get started. Can we move to the next slide? So I'm going to give a tiny bit of background on what we are. It's a user facility. So this is a very focused use case of, I just work at this user facility and I've helped with the implementation of some of these pieces of infrastructure. And we're part of the NIST in the US. It's a user facility. We get about 2,000 to 3,000 users, participants when we're running. At the moment, we're fixing the reactor, and so we're not running. This is unfortunate. It's been going on for a few years, but there's light at the end of the tunnel, so we're looking forward to coming back online. And we have about 30 instruments, and we have some pipelines that move data from those 30 instruments in a semi-automated way, and I'll go over that in a little bit. Can we go to the next slide? So this is an important part of our fair data, policies, is that we have open data by default. So users come and do experiments at our facility, and an implied and explicit policy that they comply with when they come is that as they take their data on our neutron instruments, it will automatically be made public immediately within a couple of minutes as they take the data in real time. This has a lot of advantages for them, allows them to view their data from wherever they are, whether they're at the facility or in their hotel rooms or eating dinner on their phones. And it's just open. Anybody with a web browser anywhere in the world can come and look at the raw data as it comes in. And so that's our policy for the raw data. After the users have processed it and done things with it, it belongs to them by our policy. So we host it on a self-hosted repository, which we're able to do because neutrons are expensive. And in the history of our facility, I think we have about 1 terabyte of data that goes back to about 1994 for all these instruments. And we have a DOI for that, you can see there. And so we self-host this data repository. It's an HTTP server. It's a very simple thing. And then for the more modern data files that we've been taking for the past, maybe the last 10 years or so, we've been taking Nexus compatible data on a lot of the instruments that have been upgraded to newer instrument control software. And we have some tools for viewing the online data file. So this is a synergy for, as people take their data, it becomes public immediately, but that also means that we have an online HDF viewer that they can use to look at those Nexus files and plot their data. And this can be done just by accessing the web page. And so they can look at their data and see what's happening on the instruments, whenever they need to from wherever they are. And this is useful for both the users and things like PIs and collaborators around the world. They can send the links and people can connect and look at the data as it's coming in. So this is very useful. Can we go to the next slide? Recently, we had a big push that was funded by one of our national funding agencies, the NSF in the United States, to improve our FAIR data handling at the facility. We had a good base, as I mentioned, of having open data by default, but we wanted to make it easier for users to work with their data. So we did some work to allow user-entered sample metadata that provides a little bit of history about samples that are being put in our beams. And then we provide after-the-fact search and download capabilities so they can find their data files by metadata things, like by putting information about their samples into a search field. And then we have some online tools also for reducing and analyzing the data files that are provided. So for some users on some of the instruments, they can just sit down and in a web browser do all of their data reduction and come out with a processed data file that's ready for modeling and fitting and interpretation. And then we're providing DOI. We want to make it possible to cite their data, as has been mentioned in a lot of the other talks. So we're working on DOIs for our experiments also. And then, in addition, I don't have to say this to people here, but the benefits of having metadata is that it helps other people use the data as well in these ways, context and providing citations for the authors and things like that. Can we go to the next slide? So one of the big things that we did was to integrate ORCID identifiers. So for users having persistent identifiers for every user, we have ORCID now completely part of our workflows. When people make proposals to use our beam experiments, they sign up and they can put in their ORCID. This allows them to then log in using their ORCID, and it automatically populates all the fields for finding their data and things with ORCIDs. So we're hoping to really have that be part of the core part of metadata that's included with every data set. And it even gets pushed out to the instruments so that as the data files get taken, the ORCIDs for each participant get put into each data file so that the metadata is propagated everywhere that it needs to be. And then internally, we're also switching over to using ORCID for logging into other systems for processing data internally and things like this. So it's been a very useful global identifier for our users. It's nice to have some way to unambiguously identify the users as they come through. Can we go to the next slide? And then we want to create a DOI so that each time a user shows up or a group of users shows up to do, what we call an experiment, we have, it's a defined block of work where they do a proposal and then they show up and they do the work for the proposal and take their data to take home. And every time they start a new one of these, they get a unique numerical identifier from us that gets pushed through some algorithms and then creates a DOI automatically that's pushed to a NIST DOI resolver that provides a lot of metadata about who was doing the experiment, title of the experiment, and the users can put in as much information as they want about additional metadata that's related at the experiment level. There's other metadata that's related to data files that gets pulled in automatically later on, but this is for experiment level metadata that has to do with an aggregate of all the data for this one experiment. Can we go to the next slide? So this is the outputs of what happens after the new experiment is created. This is, if you navigate to the DOI, this is what you get. It's just a nicely formatted page that shows all the metadata. And there's some search available for finding experiments through this interface. Next slide, please. In addition to experiment level metadata, we wanted to make it really easy for users to capture as much metadata about their experiments. And I think this relates to just the talk before this, they were talking about pulling in metadata automatically from as you're taking the data. So we are automatically tying sample environment conditions for the materials that are being measured. So you get fields and temperatures and these sort of things are put into a place where they'll be searchable later. So you get, and users can put in intent, which is really important when you're taking a data file. Is this a beam measurement? Is this a background measurement? Is this something that we're going to use for calibration? And so that lets them sort by intent later on. So users can put in some information about the context of the measurement that they're taking, and this gets embedded in the data file. And then they can put in, from other measurements, they can pull in any some structure, composition data, other things that they might have gotten from other measurements, and put those into a header that also goes in to each data file that's associated with that sample. And then later on, our search metadata, our search system, as each data file is pulled into our public repository, it reads out all the metadata inside our Nexus files and populates some databases with the metadata so that it becomes searchable. Can we go next slide? So there's a lot of different ways that you can find data files after the fact, by date and by participants. You can group them by intent or by things like temperature. And we also provide, of course, an API for accessing these data files, both doing the searching and then downloading them. It's just an HTTP endpoint for downloading data files, and they're all public. So you can use that in your own backend for pulling in data files and doing analysis with them. Next slide, please. This is a search page that we made. You can see just an example of looking for data by file name. You can look it up by there's a drop-down menu for just selecting one of the instruments. You get to pick which of these fields you want to use for your search. It's a flexible search form that you can add or remove fields to this to make the search whatever you want, and then it returns a list of all the data files. And then there's a button that lets you download all the files that you've found. So if you find a group of files that you find interesting, you push the download button, you get a zip file that goes down from your browser onto your computer that includes all the files that match those search criteria. Or you can download a CSV that just contains the table that's shown on the page here that says that includes all the metadata and on all the file names and all the paths to all the files, so you can do further work with that table of metadata. Next slide, please. And then you can also search experiment metadata. This is a smaller set of metadata because this is the stuff just associated at the experiment level that has to do with all the files that are taken in the whole experiment. But this is another entry point where users might come back and say, well, I don't know how to find all my data files, so I'm just going to put in my name. And that takes them to a list of all their experiments. And from there, they can search down and drill down and find all the things that they want, all the files that they're really interested in looking at, years down the road. Because we have this public infrastructure, they can go home and then, a week later when they're really looking at their data files, they can go back and pull in as many files as they want and search for files in previous experiments that might relate to stuff that they were working on. And it lets people at other facilities look at the outputs of these experiments and interpret them as they will, or let these get pulled into machine learning or AI type situations where people want to just crawl through all the data and try to understand it. Next slide, please. And of course, the search has a web page, but there are REST APIs for both of these types of search that are available for direct machine access. So the people who know about OpenAPI, it's all documented through an OpenAPI endpoint there, and so you can train, or you can set up your machine endpoints to grab information from there. Go to the next. I'm sorry, what's that?
Time is running out.
Oh, time's running out. Okay, I think this next one is the last slide, I think.
Okay.
So this is the summary. Again, we have open data by default. We're using standard identifiers where it's DOI for experiments and for data, but ORCID for researchers. And then we're trying to harvest as much metadata as we can for the samples and for the measurements as they're being taken. So thank you very much for your attention.
Great. Thank you very much, Brian. So we have time for a few questions for all the three contributions. Are any?
Do I have to talk in the microphone? Yeah. So my question is for Brian. Hey. So when you said that you have this sample metadata and process metadata, this is user defined, or do you have like sort of a template that they have to choose some fields that you have pre-prepared, or is it completely free so the user can define whatever they think is important for their experiment in that context?
Kind of both. We provide templates that people can use. So there's some schemas that are predefined sort of per experiment technique. People can choose those and then fill out the values that they want for those predefined schemas, or pull out the keys that they want to define and then apply value to it. But it's also, you can do free-form key value or free-form slightly more complicated structures in there. So yeah, it's and the process metadata, when I say process, that's mostly things that are automatically being collected by the instrument control software. So temperature, field, those get put in, but they get put into a place that's sort of a predetermined slot that's known to be, so you can find it by a well-known keyword later on.
Yeah, thanks.
Any more questions from the audience online? Otherwise, I would have a question to all the three contributors is, what would you pick from the respective other contributions as what you would like to use in your project?
I think for us, having standardized schemas, I mean, we're a pretty small shop and we don't have a lot of resources to develop full-size schemas for all the different type of measurements. It'd be nice to have something that we could just give to users to use for putting in metadata.
Yeah, I agree about schemas. It's all about the metadata. Our main objective is to be able to search across multiple different data sources. If you're going to do that, you have a much easier job if you can standardize as much as possible of the metadata. So you need some sort of tree structured metadata hierarchy where the bits that are in common are overlapped. How you get to define these standards, very difficult, but RDA can help, I hope.
So from my side, something completely impossible, which is all raw data being open. This is never going to happen in the Excel, but we're working towards have at least part of the raw data open, which comes in the new policy. But I mean, if I had infinite power, it would be all of it. Yeah.
Yeah, I agree with that as well. I've taken one note in my notebook so far, and it was, why can't we do what NIST do with our raw data? Because we don't. We have it embargoed for 3 years, I think.
And where do you see, say, options to collaborate, to work together on new things? All of you? Well, I guess metadata standards would definitely be a pick. Okay, if there are no more questions, then we can proceed to the second block of the session. That is on X-ray absorption spectroscopy data. No, not this one. And now we will go over to the Asia. No, he doesn't have. Go over to Asia, to Masashi Ishii. He will discuss the requirements for federating XAS databases. Masashi, the floor is yours.
So can you hear me and can you see the slide?
Yeah, sort of. I have a few blocks on the slides that shade them.
Really?
There seem to be other windows over them.
Mm.
Can you fix that?
So can you see all the slide in this case?
still there are some shades. I think it's a zoom. Minimize. Yeah. Much better.
Can you see the slide?
Yeah, so it's not in presentation mode, but we can see it. Just go
So
ahead.
yeah, maybe so it is better for you. So I will show the slide by this mode. Sorry, but anyway, so today, so I want to talk about the requirements for the federating worldwide disaster databases. So recently, I released the IXDB International X-ray Absorption Fine Structure Database Portal. So it is one of the answer for the data federation, I believe. So maybe so you do not necessarily this kind of information about the exhaust. But anyway, so I prepared the interesting picture of Japanese garden. So you can see the sand lip on the ground. So it is quite similar to the X-ray absorption fine structure. So the rock structure location determine this lip structure. So it is quite similar to the spectral oscillation in the dust spectra. But anyway, so today, so I emphasize the important thing. It is our community culture about the data sharing. So it has very long history. So we have no barrier to this kind of data sharing. So I want to realize this kind of data sharing global scale. So just now, so our community is going to global cross-differencing of the spectra. And also, our recent machine learning trend provides the requirement of the metaspectral analysis. So in that case, we have to analyze so many data simultaneously. In that case, we need data federation worldwide. But still, we have a lot of barriers for the data federation. So I think the first barrier is vocabulary fluctuation, especially for materials name. And the next barrier is various table format in databases. Is quite a serious issue. So this morning, so we see a lot of service, but they have different data structure and strategies. So it is difficult to combine, but so we have to do that. So, and the third issue is usage license. Maybe so in the fair case, so there's no problem, but sometimes we have to consider this kind of license issue. So today, so I want to define the requirement for the data federation. The first requirement is vocabulary unification, and next requirement is knowledge unification. So I recently released the International X-ray database portal, as shown here. So it is an implementation example. So please access to this service by using this QR code so you can understand the situation of the global cross-referencing state. So here is a brief summary of the IXDB International Disaster Database Portal. So the IXDB is located in the center of this figure. So users input the material name as query parameters. For example, in the kappa case, so the user normally use various name, for example, kappa foil, CU, kappa or something like that. But so we prepare the dictionary for the material's name. So our dictionary provides a unique ID. For example, in this case, Q1426. So it is the ideal ID for the copper. The IXDB uses the unique ID for to get the knowledge. So we access to the other endpoint of the knowledge base. And so in this case, it simply get the URL and facility name for each database. So the portal provides the URL, and user can access to each database by using this URL. So anyway, so this knowledge provides a single algorithm for global search. So this is the first requirement answer for the compiled Zast dictionary. we recently released the materials dictionary matbook in NIMS. So it is a very useful database, control the vocabulary fluctuation. So here is one of the example of zinc oxide. So we have a lot of material name, for example, zinc white, Chinese white, or ZNO, something like that. But the dictionary matbook provides a unique ID. It is URI, and a normalized material name. So in this case, Q1800 is a unique ID for zinc oxide, and zinc oxide is, of course, a representative name. At this stage, so the vocabulary size is not so large, but we cover the 5 databases around the world. The materials number is about 1,000, and the synonym of them are about 8,300, and the chemical formula is 850. So about 10,000 words is used for the data fluctuation conversion. So now I want to say the next requirements answer. So we create the ZAS knowledge. So maybe so you can understand. So we have several databases around the world, and so now our target database is 5, as shown here. Of course, these databases has different data structures, so we need some common concepts for the database. So in our case, of course, we deal with the exas. So in that case, we normalize the concept with thus concept. So now, of course, we can use a machine readable technique by using ontology. And so I have no time to details about the ontology, but anyway, so we normalize the thus concept by using this schema. And also, we provide additional information, for example, data license and data folder or actual URL, something like that. So we can use this kind of schema for the data search by using a singular algorithm. So here is a implementation of the idea of this IXDB. So now our target database is 5, but so it will be increased after this conference anyway. So our MDR ZAS database in Japan is a federation type database, and the backyard of this database, we have 6 institute data. And so we integrated their data in the one place. And so we have about 2,000 data in this database. And the shared frame database is very unique because they have also other federation with other spectroscopy. And so a rich research data is involved in this database. And thus leaf in US, it is very clean and a sophisticated database with using some XDI format. So we can get the XDI files from this database. And fourth database is China. So Chinese database is experimental ZAS database. So it is quite new, but so they have original data about the battery and actinoid. So it is very unique for us. And the final database is Italian database, RDA database. So it is compact, but we can download of the data by using XDI format. So anyway, so that's kind of database is federated on the IXDB portal. So now, so we can provide this kind of statistics of the IXDB. So linked database is 5, and the MDR has 2,000 data, and the shared frame 500, and the ZAS leaf is about 300. And Chinese and the RISA database also provides several data. So total spectra is 346. So absorption element is 64, so lithium to uranium. So it is very wide range, and absorption H number is 100 to 18. So the maximum data number of absorption H is around KH over the 300. So please access to this IXDB portal so you can see the this top image by using this QR code, and you can understand the federation of the data around the world from this database. So anyway, so I'll summarize my talk. So requirements for the federation is vocabulary unification is and knowledge unification, and also we realize one service IXDB at this site. So this is all for my presentation. Okay, thank you very much.
Thank you very much, Smadashi.
Yeah.
So the next speaker in the row would be Christopher, who will present the RefSAS database which is developed within the framework of Daphne.
Yes, thank you, Rolf, and thank you for this organization of this session here. And yes, adding another database to the pool that we have already seen right now, I will present now the current work of on the RefSAS database that is within the frame of the Daphne for NFDI consortium, also from Germany. And actually, four institutions are contributing to that. This is in Karlsruhe, the university where I'm from, Technical University Berlin, and from Wuppertal University and DAISY as well. And next slide, please. And yes, so just to give a bit more background on the idea of our database was that for this technique, X-ray absorption spectroscopy, there's a lot of approaches in the analysis that use or rely on reference data, so data from a reference spectra or reference materials that are then utilized to analyze your data that can, for example, be mixtures of different species and so on. And to not have to always remeasure all these samples, this was the idea of this database, to like then have a database that already has the spectra of these reference data, but then of course this sets really high requirements for the spectral quality, but also for the documentation. So that means the metadata of these spectra that then are online, so that you can really rely on using them for your analysis. Next, please. So this is just a short view. I mean, the website for, so the database is in operation. There's a website for that, and you can go there, and there are not a lot of data sets yet, because there's a point I will come back later on concerning the hosting of the website, that we have some challenges there still. But the next slide. We have like on GitHub really the source code is open there and the documentation there, so you can really have a look on how the source code for the database and also the quality control that I will show later bit on is working. So it's not about only the FAIR data, but also the software that is behind that. And next slide. So this is like really the workflow it's really the idea is really that users can upload the data in this database. It's not only a database that is for spectra from our institutions. And you have really these 5 steps that I want to show you here, and then there are some that I will want to go a bit more into detail. So first is really that there needs to be a user login, and he or she can choose then to upload data set, and there's also some different data formats can be digested there, also some standards from different beamlines from these large-scale facilities, and also for some laboratory spectrometers. It's actually what I'm working on. And so you can see there's still a variety, and not really, there is a principle, there's some standard, but that's really based on not everyone is really using it. And so this is a really bit harder, but in the status quo, we have decided to like implement digesters for different kinds of data and different data formats, and also data structures. And then the user gets a preview of the data and can like add or edit of the metadata files, but they're also like extracted from the file if it's like according to one of the standards that are already defined. And then he can or she can verify the data set to be like uploaded, and this is then going to the metadata file storage. And the next part is really, this is the quality control. So the spectra here, as we wanted to say, as we said, we want to like set up a reference database. We really relying on good quality of the data. So it's there's an additional step. That's not like every data is like shown, but there's some quality control, some automatic checkup, which is then afterwards going to a human curator, and he's really then in that case, he is really a he, and he's then saying, if this spectrum is fit to be like uploaded or visible on the website afterwards, and so be visible and then downloadable for all the other people. And then downloads from this data set can be in the original data file format, but also in the HDF5 data format according to the Nexus standard that is currently being worked on. I want to show on the next slide, next 2 slides. Next, thank you. But currently, what are the metadata files? We group them into different fields, and I mean, we have heard a lot about all these, but one point I want to highlight is here, and usually this is a technique that is performed at large-scale facilities, so these synchrotron radiation facilities. But in like the last 10 years upcoming, there was also like a development of laboratory-based spectrometers for this technique. But they produce completely different data, and not only in terms of raw data, but the data processing is also quite different from this data. And so like there's not one metadata scheme working for all these. And additional to that, even at the beamlines, at synchrotron radiation facilities, you have different acquisition modes that also produce different kind of data. And you need, of course, to know about all of these when you want to use these data afterwards. So we set up a first draft for also this laboratory that were not existing actually for a long time, and the spectrometers, we set up a first metadata scheme that we already implemented, but we of course working on this to like further develop this. Next slide. And this is some slide, as I said, there is a Nexus, we have heard about Nexus, there's a Nexus application, the definition, the NX-XAS for that technique, but this is, I would say, quite outdated, and there's now a group where also some of this that are here within this project that are in this group to discuss propose a new Nexus definition for NX-XAS that like includes not only also like developments that have been done at the synchrotron, but also to include then these laboratory metadata files for process data. And so the second thing I want to show you is about the quality control. I said it's important. Why is it important that I want to show here? I mean, you can see here that is the spectra that you can see here is like from the same sample. It's a platinum foil, but it was measured at different beamlines. And even if they are small, there are differences. And when you, of course, want to rely on this data, you need to know where are these differences coming from. And so we like integrated an automatic quality control that of course is then only a suggestion afterwards. So we define some quality parameters and like for like how's the absorption jump, so the height, and I mean I don't want to go into details of these, but there are some quality parameters that are defined, and then there are ranges defined where they should be within. And if like these quality criteria are not met, then this is flagged, this data file, and of course the curator has decided in the end then if this is a valid data file. And okay, next, yeah, already quite fast. Short summary or more an outlook. I said in the beginning some problems or challenges that we like still working on is really long-term hosting of the infrastructure of this database. I mean, of course, I mean, we all have the problem of like funding also that is usually not for a long time. And I mean, within the universities of Germany, we don't have the staff or the funding really to, or the infrastructure, also IT infrastructure to host such a project that should be then like really long-term active. And of course, we don't want to, after the end of this project, just to say, okay, well, that's not the idea, right, of these FAIR data. And so we are, and really the idea here in the end is then that is hosted by one of these large-scale facilities, because they, in principle, have the stuff, they have the IT infrastructure, they have the capabilities for the authentication process and for login and so on. And one thing maybe to add, the data is like the amount of data is really low here. Of course, the spectra are 2-column spectra usually, and some metadata for that. So it's not big data. It's really just like really long-term hosting that's a problem. Then this, when will be hopefully not that long in the future, will be this new Nexus definition for NX-XAS, so for XAS experiments. Of course, we want to then implement it, but it's rather easy in that approach. And yeah, we still have to like include the comparing feature of different samples that we have. As now you can only view one of the files and one of the things. And yeah, and one point here down there, what also was mentioned before, is that like the licensing problem, we also had a longer discussion. What is the license for the data? And in the end, we decided for the CC BY 4.0, and the user has to like really agree to that the data might be under or are under this license in the end, and so then can say that they want to upload it. Next. And just to see, I mean, I've run through this, of course. I mean, there's a lot more technical details and so on. There's a paper that was published recently, and there you can also get get the contact information of us to get in touch with us. We were really welcome for input in that, of course. And and next slide. There's one last slide, and I think I really want to say this. I mean, this is of course not the work of one person or so, and I really want to highlight these three guys, as they are the ones that mainly did most of the works from these three institutions, and for like really doing the programming. And actually, the one in the middle is the one that is still more or less privately hosting this database up to now, because there's not a solution yet for this long-term hosting. So he set up a Amazon web server in the beginning, and I think it's now moved to another. But yeah, and of course, I want to thank the whole consortium and the funding within that by the DFG. Thank you.
Yeah, thank you, Christopher. For the next contribution, we jump back to Masashi, who will give us more, details of one of the databases that he already referred to. And Masashi, please continue.
Yes, can you hear me?
Yes.
Okay, hi again. Next, I want to talk about linkage with the European database with our Japanese database, MDR-ZAS database. So here is the background work, our work, Japanese activity, MDR-ZAS database. So it is open, and so you can access to this database by using this QR code. But anyway, so it is integrated type database, and now 6 institute is joining to this project, and they provide their own data, and I integrated these data in one place, materials data repository in NIMS. So now we have 2,263 database data in this database. The main feature is open access, and we assigned DOI to all spectra, and all data has machine readable metadata, so it is very useful to access by using machine. And also, we can search by using normalized material name by using dictionary. And also, all data is downloadable, and you can also use API for data-driven applications. So today, I want to talk about the outside linkage from EXAS. So this is advanced usage of the dictionary of Matbook. Matbook is our materials dictionary, so vocabulary control. But anyway, based on this Matbook, we use vocabulary management, but the main application is MediaWiki. It is very, very famous application, and actually the MediaWiki is used for the vocabulary management of the Wikipedia. And the advantage of this MediaWiki is assigning of URI to each chemical materials. And also the MediaWiki provides a machine accessible endpoint, Spark endpoint. By using this MediaWiki, I try to linkage with crystallographic open database, COD. Here is the actual figure of Matbook on the right side of this slide. This is the example of titanium dioxide with rutile structure. So of course, we have a unique ID of Q1743, and this vocabulary management system also provides a broader concept as shown here. So in that case, we provide the wider concept of oxide for this titanium dioxide. Also, we provide the COD ID for the crystallographic information, but please find the space group is also provided as a broader concept. So it is very useful to screen the data by using broader concept. So maybe the crystallographic open database is very famous and you use this kind of database, but it is a European database, and so they cover a wide range from organic, inorganic materials, organic to inorganic, and some composition materials and minerals. About 500,000 data is available on this database. And basically, so we can download all data, and almost all data has zip file, and the data is public domain, so it is very useful for the machine learning. But anyways, now we connect the MDR-ZAS database to COD database. So here is the actual data linkage on the IXDB portal. So first, maybe so you use this portal for the material search, and you can find the spectral linking list on the top of this search results. But below that, so you can see the linkage to the crystallographic database with the space group. So you can, when you can click the space group, so you can obtain the COD ID list for the space group. And the COD ID list provides the actual page of the COD database as shown here, and you can download the zip file from this original database. So now, so we have a 631 materials linkage in this database. So it is very useful for the middle class data structure ordering in the sample. And so actually, so we have about 5,000 crystal structure by using this strategy. Of course, the ZAS database is strong linkage with Japanese database. So here is the data sharing list. Some overlap list with the Japanese database. So now we have 6 institutes as a provider. In this case, the Shade Frame database in France has a strong overlap with the Japanese database as shown here. For example, the Spring 8 data has about 160 overlap between the French database. So please understand the overlap is not negative meaning. So because the all spectra has different optical resolution and the experimental condition. So all of the data can be available for the referencing of the experimental results. So totally 400 data is overlapped with the French database. And considering the shade frame database has about 500 spectra, totally 900 spectra is available for the shade frame users. So it is very useful for the shade frame users. And also, so please understand, so the shade frame database has original data, for example, chondrite data. It is quite unique, so we cannot see this kind of data in other databases, but it is very useful for the space physics. So this kind of original data and data sharing is provide new material science by using this scheme. So here is another example of LISA database. So the LISA database is a very compact database. The spectral number is 50 about. But so on the other hand, so the overlap between the Japanese database is quite large. So the number is about 300. So LISA database user can use about 6 times larger data by using IXDB. So here is the overall picture of IXDB. So now, of course, we have 5 ZAS database linkage on the IXDB. And yellow highlighted database is linked to, from the Europe. But so please find the dictionary is also used for the data linkage outside of ZAS. So actually, now we can access to the crystallographic data by using dictionary. And also, I have never talked in today, but we can going to materials project data by using dictionary, so you can check it from the IXDP portal. Also, so Hackspace data is linked with by using ontology level. So because the X-ray absorption and Hackspace is quite similar physical concept, so ontology can be used for the data linkage to this kind of to other synchrotron radiation experimental database. But anyway, so our next cooperation with the European database should be reference thus, lift thus. So from Daphne. So it is good presentation in previous presentation. So, but anyway, so it is the next target. And also just now we are trying to the data federation with the Canadian light source. So we will release this kind of linkage in near future. But still, we have some future issues as shown here. So the first issue is compiling a materials dictionary for complex samples. Normally, so the standard sample is used as a reference, but still we use very complicated structure in actual research. So in that case, we have to make a dictionary for this kind of complex materials. And also a harmonization with international efforts to unify the metadata. So, so now the international community making a unified metadata format, and so it will be released soon. So we have a long discussion, but in future we can use this kind of unified metadata around the world. So in that case, we have to use this metadata for the search index in IXDB as well. And also, when we consider the machine learning by using the spectra, so we have to deduce, we have to so pick up some raw data from each database. So in that case, we need a common API system. So the common API system provides a common query parameter, and you can easily use this API to get all data. So that kind of thing is ideal, but so we have to do a lot of work for to realize these kind of issues. Anyway, so I provide this kind of IXDB under the FAIR principle. So we are looking forward for collaborators to develop this specific example together. Okay, thank you very much.
Thank you very much, Masashi. Again, all the three contributions are open for discussion and for questions. Are there any questions in the room or from the audience online? No, Masashi had two contributions. So.
Because I have a question for Brian, actually, because I was playing with his API. Would that be okay? Yeah, sure.
We could first discuss XF cases, and then we have a general discussion anyway.
Hi, Masashi. Thanks for
Hi.
pointing out on your database. You were showing that. Yeah, can you hear me?
Yeah, sure.
Okay, perfect. Good. So you were elaborating on your database, and you had in your very last slide already some ideas on how to link to the Daphne reference database. So what would you think would be the very first step to start on this?
So it is just vocabulary management. So if you provide the material name, so we can make the material dictionary with our data, our vocabulary management system. So there is no high barrier.
I mean, that kind of links already to a question that I would put. to Masashi, you refer to vocabularies on, say, materials.
Mm.
Are these vocabularies developed at you in-house, or is that, say, standardized worldwide, or I don't know?
Yes, so I made in-house, but so our target is worldwide. So yeah, of course. So I search a lot of vocabulary, but so anyway, compiled by myself.
Yeah, I would suggest, I'm not an expert in that field and I'm wild guessing, to be honest, but I would assume that these chemical societies would already have some sort of vocabularies for several things. So it might be interesting to link your vocabularies to other existing vocabularies that already exist.
Yes. So yeah, of course. So this kind of so data merge is very important to reach the vocabulary. But I think so it is not difficult. So actually, so we combined with other large database, for example, PubChem, by using API. So this kind of linkage is available now.
Okay. More questions? Otherwise, I would still have another question, maybe a nasty one to Lisa. No, because Christopher, you mentioned your hosting problems. And isn't that a case for the I in NFDI?
Sure. Yes, I mean, that's what all of the projects in NFDI are working on, right? And in a first step, we need to identify all of these problems, and this is a huge one. I totally agree, and it's a, yeah, it's a mess, and it's very sad that this issue could not have been solved already. But I think we are on that. Yeah, we are on the way. So yeah, I'm pretty sure that we can solve the issue soon. And then this will also, let's say, be a use case and some way of solving all of these issues, at least in the Daphne project. And then later in the NFDI, also other people can can learn from this, right? And this is why we have those projects. I mean, it's not meant to be perfect from the very first day, but it's meant to be get better within time, right? And I think we can approach and achieve that. So that's fine, right? So not a nasty question.
Yeah, I guess we should more pushing on the NI on in NFTI in general and to more request, say, permanent infrastructures, not just projects. But I would transition to the general discussion by that remark, and then we come back to your question.
Yeah, extremely silly, but I was because I really like the metadata catalog that I see from Brian's talk. I've been playing with it a little bit, and the research bar is nice. It's something that we do not have in my MDC. I mean, we do have it, but it's quite nasty. I don't know how it is in Scikit. But I'm wondering, because in the API, I can see one can search per title, and in the user interface, they cannot. Is that a reason for that?
Probably not. As I mentioned, we've been down for a while, so we haven't had a lot of, sometimes the rough edges get worn off when people start actually using it. So no one had noticed this or mentioned it to me yet.
Okay, it's not there, so I mentioned. No, I'm just wondering because we're also dealing with searching through metadata in the X file right now, and one usual request from the users is, does this string contains this for this one column? And it happens all the time for us, and so yeah. But anyways, that was it.
Thanks for letting me know.
Any more, say, discussion contributions, opinions, statements? Maybe also not from the online auditorium. Otherwise, say, I would ask maybe all the presenters on how do we proceed from here? So what would be the next step for more collaboration?
I mean, my question was already pointing to that, right? So I think we have a very, very nice opportunity of collaborating with Masashi and the Daphne project, right? So we have the reference database that could maybe be included to your general
Yeah,
database. I
sure.
think this is a really nice point to start from. And to work on this, I guess we should get all of the people working on both projects into one virtual room, probably. And then yeah, and we are already working on that because there will be a talk in Daphne by you, Masashi, and then there will be lots of discussion. So I'm quite confident that we can get this going, and this would be a great outcome of this session. So I really like that.
I agree with you. So maybe we have a discussion next year, so we can progress this kind of project.
Yeah. So he just said nothing to add. So Christopher is with us as well.
Yeah, and please include us in the invitation, and I'll pass it on to my colleagues who are doing XAS. Yeah.
Yeah, just to mention, we are in a project with Abraham in the Xide Foxas project, with one of those Oscars projects that are yet now about to start, or in theory started the 1st of October. Anything else? We have still 9 minutes to fill.
If this project's going ahead, is it worth the overhead of trying to do it as a working group in RDA? So spin out a working group from this interest group, or it does have a certain overhead to do that. Maybe it's better just to get going, but it's worth thinking about.
I mean, what would be the scope? What would be the work program for
Write down a plan. It would force us to write down a plan, which might be something that be a good thing to be forced to do.
I guess the plan anyway needs to be written down, right? So maybe it's maybe we can all meet in a virtual room of RDA, and then that's the working group, right? But you're all more experienced with RDA than we in Daphne are. But it would be a great point to go to and to start from this session. So yeah, why not?
I mean, that is what these working groups are, virtual rooms to sit together and to work on something.
It would be an opportunity to bring others in as well, if to broadcast it a bit wider.
Yeah, and to get to some sort of standardization that has, say, that approval as an RDA recommendation, which has some sort of weight. Otherwise, well, since we doing publications or advertisements, as we mentioned samples in the session. There will be both tomorrow in breakout 4 on the question whether we need a vocabulary for the sample type classification. And yeah, that would also be probably an interesting, say, project that would be probably in the interest of the Photon and Neutron community. Yeah, if really nobody raises his voice, and
I was about to ask you afterwards, but quality control, that's something that I got a little bit confused on, because in your slide said automatic, and quality control automatic makes me shiver a little bit. So how is this actually done? I mean,
I can comment on that. It's automatically, I mean, it's like doing the evaluation and extracting some parameters and looking if it's inside these ranges, but afterwards is you always checked and maybe redone manually by an operator. So it's just like, No. There are some. I mean, there are some ranges that are defined to be well parameters for good spectra and such. So, like for this jump height, should be like this amount in this range and so on to be data that are, yes, but they are defined by our people. I mean, there are some. There's not like a international recommendation. What is these ranges? So it's really like we decided on these parameters, but in the end, it's checked again by the curator.
Yeah, I don't know, Heike, if you want to ask your question yourself and maybe elaborate a bit more on that. If you cannot talk, I can also do it for you, whatever you prefer. Just give me any sign. Okay, she can't talk. Okay, so she was just asking whether the EXAS database basis can be a blueprint for other techniques. What do all of you think?
I can say something about just a technique that I do a lot is reflectometry, and we've looked into. I think there are some techniques where you can describe your data and the models in a sort of a closed form, and then there are some techniques where that's very difficult. And reflectometry is one of those where it's very hard to write down a model in a closed form with a schema that can be defined ahead of time. Like models they just get very complicated, and yeah, we've struggled with that.
Yeah, I think also, I mean, all techniques are quite unique in that case. I think it's more, like you said before, it's like we found a way to tackle these challenges, and that might be helpful. I mean, it's not like really the solution that would be helpful probably for other cases, maybe to some amount, but it's like the way to go there, and what's been challenging on the way.
Yeah, I mean, my personal take on that would be, first of all, yes, of course, that could be a blueprint. But I guess we should move technique by technique, because all the techniques are different, and what they do provide and where the challenges lie. And of course, we will learn with each of those steps on how to tackle these kind of problems in general. Okay. Normally we have 1 minute in the session left, but well, I just close the session with this one. And thank you very much all for your contributions. It was a very nice session and nice audience. And yeah, thank you.